Hello, students. Welcome back. Dr. DA again. And this is the third in a series of lectures from unit number 8. We're trying to explain and apply the quantum model of the atom, specifically as it applies to electrons and how they are arranged in a typical atom. So for this lecture, we're going to take up on the topic of the periodicity of physical properties of elements. We saw in the previous lecture that elements are lined up on the periodic table, and their placement on the table tells us about their electron configuration. So it's kind of logical to assume, therefore, that the electron configuration of elements plays a major role in some of their properties. So we're going to talk about just a couple of them. First of all, we're going to talk about physical properties, all right? Remember that the way the element atom is constructed from our viewpoint, and again, it's not that it's done this way, but one way of visualizing it is I take a nucleus with the proper number of protons and whatever neutrons that isotope has, and then I bring in a prefabricated shell of electrons that is the same configuration as the previous noble gas on the periodic table. And then on top of that, I add what we call the valence electrons, the ones that are at the highest shell, the highest value of N. These are the ones that are farthest from the nucleus, and therefore, in many ways, they kind of define sort of like the extension, the boundaries of the atom in terms of saying, well, that is kind of like about as far as those electrons are going to be oscillating within their wave function. There are several ways that you can use to sort of get an idea of the sizes of atoms. So we're going to look at some of them here very quickly. For example, let's say you have a solid metal. Well, in a solid metal, we can sort of know that they're arranged uniformly. So if we have a way of measuring the distance between the nuclei, in other words, the cores of each atom, and we take half of that and we assume that's the radius of that atom. Remember, we are essentially approximating the atoms as having a spherical shape. For non-metals, we might be able to look at a diatomic molecule, and although the electron clouds might be somewhat blended, we can approximate perhaps, again, half the distance between the nuclei as being the radius of that. For other elements that do not form diatomic molecules, we would probably have to look bond lengths of different compounds and then calculate like a statistical average, all right? What are the techniques for these? Well, there's different forms. One of them we're going to study later in the semester, which is called X-ray diffraction. It's a method that allows us to calculate several parameters, particularly with solids, all right? Okay, so let's say that I had a way of measuring the sizes of different kinds of atoms of different elements. And I'm going to plot that radius in picometers against the atomic number. And I would get a pattern that looks like this. And again, at first it might be daunting, but what you notice first of all is you see that there is a trend of spikes followed by downward trends. Notice that in each section, the spike seems to be formed by actually a group 1 element, lithium, sodium, potassium. And then as you increase the atomic number, in other words, as you scan from left to right in that period, you see a downward decline in the radius, in other words, in the sizes of atoms. Perhaps this chart is a little more helpful. Here what we have is we've kind of put them to scale on the periodic table. And again, we're going to talk here mostly about the so-called main group or representative elements. In other words, elements that fall into the S and P blocks of the periodic table. I'm not going to include the transition metals in here. Again, notice that, first of all, look at the first group there, from lithium down to cesium. Look at the second group, from beryllium down to barium. Go to the other side of the table and look even at the noble gases, from neon, argon, krypton, all the way to radon. What do you see? Right, you can see that within a group, as you go down, you have an increase in the atomic radius. In other words, the atoms are bigger and bigger. Now, if you look at a given period, the trend is a little different. Let's focus here on period 3 with sodium, period 4 with potassium. Notice that as you go from left to right, okay, even though the number of electrons is increasing, right, because the atomic number is increasing, the sizes of the atoms are actually decreasing. So that's a very interesting trend. So let's look at the two trends we just discussed. First of all, within a group, an atomic radius increases as you go down the group. Well, it makes sense. Remember, as you go down a group, the value of n for the valence level increases, which means that the electrons that are farthest from the nucleus are even farther and farther away as you go from n equals 3 to n equals 4 to n equals 5, right? So it makes sense, therefore, that because the valence shell is farther from the nucleus, the atoms would look bigger because the electrons are capable of oscillating in that, wave function slash cloud a little farther away. Now, the trend that is interesting is the one as you go from left to right along a period where we see that the atomic radius decreases. And the reason for this is a phenomenon called shielding, which we discussed earlier, and what is called the effective nuclear charge. So let's work with a few definitions here, okay? Um, First of all, let's say that, as we talked about before, electrons that are near the nucleus, in other words, electrons in the core shells of the atom, can shield outer electrons, i.e. valence electrons, from the attraction of the positively charged protons, right? We saw that, for example, in the case of s versus p orbitals. Electrons in a 2p orbital are kind of like shielded from interaction with the positive nucleus by the electrons in the 1s subshell. However, because electrons in the 2s subshell can penetrate, in other words, they have a little blip of probability closer to the nucleus, they are able to bypass some of the shielding and therefore have a lower energy. So in this case, it's similar. We're going to consider, again, the atom as built with a nucleus and then a core of electrons that are similar in configuration to the previous noble gas. And we're going to say that those electrons are capable of shielding the valence electrons from their interaction with the nucleus, all right? And what we're going to do is we're going to make a definition here. We're going to say, what is the actual charge, the actual positive charge that an electron, quote unquote, feels? We're going to call that the effective nuclear charge. And we're going to say that essentially the effective nuclear charge is whatever the atomic number is, in other words, the number of protons or positive charges minus some kind of a factor. We're going to call this factor the shielding constant, all right? And we're using the, this is kind of like the small case or, small case version of the letter sigma, the Greek letter sigma, all right? And a scientist, John Slater, came up with a formula. And it's one of these empirical formulas. In other words, it's one of these things that you kind of like hammer out mathematically and kind of make it work. And it's called Slater's rule. And it says that the way you calculate this sigma, the shielding constant, is you take however many inner or core electrons there are multiplied times 0.85. And then you add 0.35 times the number of other valence electrons. In other words, I'm going to calculate the effective nuclear charge and the shielding constant for a specific electron, so one electron at a time. That electron may or may not be alone in that valence shell. There may be other ones. And if there are other ones, they are also going to contribute to some of this shielding, all right? So I'm going to look here at this sequence of elements: sodium, magnesium, aluminum, and silicon, okay? Notice that these are all in the so-called, in the third period of the periodic table, all right? So let's look at the atomic numbers first of all. So sodium is 11, magnesium 12, aluminum 13, silicon 14. Now, what they have in common is that they all have the same core assembly, the prefabricated shell, which is neon, right? Which has 10 electrons. So each one of these has a core of 10 inner electrons, all right? So let's calculate the Slater's rule effective charge, okay? I'm gonna go here to our, okay, here we go. Let's go to this thing here. And again, I'm gonna take the liberty of using here the lined paper. So let's consider actually, you know what? Let me use the same one that you have in here. Let me use that. Okay, here we go. There we go. That's the same slide that you guys have in there. And we said that the core electrons here are 10, right? Because all of them share the same core that looks like neon, all right? So let's calculate this thing. And let's say that sodium has 11 total electrons, okay? So that's 10 core electrons and 1 valence electron. We're going to calculate what is the effective charge for that guy. So what is the effective nuclear charge for the 1 valence electron in sodium? All right. So we said that the effective nuclear charge would be the actual number of electrons, atomic number, minus this sigma value here. All right. So that would be 11 minus, let's see what sigma is. We said is 0.85 times the number of inner or core electrons. So 0.85 times 10. And then we're going to add 0.35 times the number of other valence electrons. Notice that it says here other, right? Just want to make sure that we understand what we're saying here. In other words, it's not the total number of valence electrons, it's the other ones. Now, in this case, since we only have 1 valence electron, this would be essentially 0 because there's no other valence electrons, right? Right? No other electrons in here. Okay, so what does that give us? So that'd be 8.5, right? This would be 0. So 11 minus 8.5 would be 2.5. All right. So in other words, that electron in the valence level of sodium does not feel all of the charges of the 11 protons in the nucleus. It only feels the equivalent of 2.5. What does that mean? Well, it means that that electron is not as strongly attracted to the nucleus, and therefore it has a little more freedom to roam, to expand a little farther away than it would if it were feeling the full attraction force of the 11 positive charges in the nucleus. All right. Okay, let's do this. Let's do potassium. I'm sorry, magnesium now. Let's do magnesium. Okay, so magnesium would have 12 electrons. So that would be 10 in the core and then 2 in the valence level. But what we want to do is, what does 1 valence electron, quote unquote, feel? In other words, we're going to calculate the effective charge for 1 valence electron. All right, not for the two of them, not the average, just for one of them. What does one electron feel like? All right, so what would that be? So that would be the, again, right, Z minus sigma. So that would be 12 total electrons minus, again, 0.85 times the core electrons, which is 10, and 0.35 times, well, in this case, remember that we have one other electron in here, so we're going to put one in there. Okay? So that's how we calculate the effective nuclear charge that is felt by one valence electron in here. And what we see here is that this now becomes 3.15. Don't worry about sig figs here or anything like that. We're just going to build a little table. Okay? Let me give you a few seconds to make sure that we understand what we're doing here. Remember, we're calculating what is the actual charge that one valence electron feels in its location given the number of core electrons and given that there might be other valence electrons around. Remember that valence electrons, because they're in the same shell, they might cause a little repulsion against each other. Okay? Okay, so now that we have that, let's come back here to our table and let's fill it up. Okay, so we did these guys, and so we did sodium at 2.15, magnesium. If we keep doing this here, what we're gonna find is that as we go from left to right in the periodic table, we see a progressive increase. You can see a progressive increase here in the effective nuclear charge. So a valence electron of silicon is feeling a stronger charge from the nucleus than a sodium ion is. Therefore, an electron in the silicon valence shell gets pulled in a little tighter into the nucleus than an valence electron of sodium. As a consequence, if you draw the boundaries of that electron cloud, you'll see that it makes sense to think that as you progressively move from left to right in this period, you're going to have stronger effective nuclear charge and therefore electrons getting pulled in closer, resulting in a smaller atom. And therefore, that's what you see here. As you go from left to right, you have a decrease in the relative size and the radius in picometers of these atoms. So again, notice that the majority of the electron sharing, you can see from the formula here, 0.85 times the number of core electrons versus 0.35 versus other valence electrons. You can see that the majority of the shielding comes from the actual core electrons. These are the ones that are kind of blocking off, kind of like shielding the outer electrons from the fullness of the positive charges in the nucleus. Okay? I hope that's clear. So let's look at this table, gives you the trend. Again, within a group, as you go upwards in the group, you have an increase in the nuclear charge because the electrons are closer to the nucleus, feel the attraction stronger. As you go from left to right in a period, you also have an increase in the effective nuclear charge, and therefore electrons get pulled in closer, and you have a decrease in the sizes of these guys. Just a quick comment here. I don't think this is as important, but if we look at the transition metals, for example, let's look here at the period 4 transition elements. One thing you notice is that although the trend continues of decreasing size, it is not as dramatic as it is for the main group elements, all right? So it's a slight decrease, and then it kind of sort of levels off, and then it comes back up again as you go from left to right in there. So let's explain that. Now, the one thing that is true is that if you compare transition metals, let's say in period 4 with period 5, you can see that there is progressively an increase in the size, just like it was for the regular main group elements. And that makes sense because as you go down, you have a bigger N value, in other words, in a valence shell that's farther away from the nucleus. So it makes sense that they'll increase in size down the column. Now, why are they roughly the same size across the D block? Well, the idea is that in this case, the actual valence shell, in other words, the electrons that actually are farthest from the nucleus are actually in the S subshell of that level, not the d electrons. The d electrons, remember, their n value is one less, so they technically are not valence electrons. They're not the farthest from the nucleus. The question is, do they contribute to shielding? Well, the fact that there's not a whole lot of change from left to right within a period in the transition metals tells us that electrons in the d orbitals, yeah, they just make a small contribution to shielding. And so because of that, the effective nuclear charge on those electrons in that, S subshell, it's about the same. And so it doesn't change much. Uh, slightly, there's a little spike when you get back to the P block, because at that point, those electrons are slightly extended. And so you have a slight increase, and then it decreases again as the nuclear charge increases. All right. Another question that we can ask is, what about ions? What happens with ions? So here on the left, you can see the group 1 elements from lithium to cesium, and then their relative ions. And the trend is obvious, right? Remember, if I have, for example, sodium, and I make a sodium ion, what I'm doing is I'm removing an electron from the outermost shell. That automatically means that I am dropping down to the isoelectronic configuration with with a neon atom. In other words, I should have less extension of those electrons, therefore a smaller atom. Now, with the nonmetals, you can see, for example, for the halogens, from fluorine, chlorine, and bromine to the respective negatively charged ions, once more, since I'm adding an electron to the outermost shell, and that outermost shell was already, compromised because the nuclear charge was effectively not as good. Now I'm putting an electron there that is compensating for that extra, effective nuclear charge. And that allows that electron, by repulsion with the other ones, to extend a little more. And so we would expect that the corresponding anions will be bigger. So I guess the rule of thumb is that if you are to make a ionic compound, let's say between lithium and fluorine, what you can see is that the cation is always going to be smaller than the atom from which it is formed, and the anion is going to be larger than the atom from which it was formed. So it's kind of like they reverse sizes in this case. Okay, so of course there are other physical properties of elements, but we're not going to consider those right now. We're going to jump ahead and talk about chemical properties. All right, maybe give you a few seconds, maybe to take a little break if you need to. And if you want to pause the video here for a little bit and then come back. Okay, we're back. This is the second part of this lecture. Now we're going to talk about the periodicity of chemical properties. Now, we're going to have to review a few things first of all. First of all, here's one observation that we make. Elements in the same column typically have similar properties. So for example, the elements in group 2A, the alkaline earth metals, they are metals. The halogens, they're non-metals. So they behave differently. Metals make cations, non-metals make anions. Metals typically form ionic compounds. Halogens form some ionic compounds, some molecular compounds. So you can see that the properties are rather similar within a group. Now, what's interesting is that within a group, we are going to see a periodic increase or decrease in different kinds of chemical properties. Let's go back, for example, to the metals. You remember that back in Unit 4, when we talked about redox reactions, we built this chart that we call the activity series, right? And remember that this was built on the basis of how does a metal react with, let's say, water or with an acid. So if a metal is very active, it will react with just cold water to produce hydrogen. We said that was essentially a redox reaction. As you can see on the left side there, what is happening is we're measuring the ability of that particular metal to form a cation and therefore transfer an electron that reduces the hydrogen atom in water into hydrogen gas. Now, what's interesting is that just like the table says, if you go from top to bottom, lithium to sodium to potassium, look at the difference in activity here, right? Look at the difference in activity. Lithium gives you hydrogen gas. Sodium gives you a very active reaction. It combusts. Potassium will throw up flares like fireworks because it is so active. So we can see that trend, right, as we go down the periodic table. And we call that the metallic activity or the metallic character of atoms. You can find a similar pattern if you go to the group 2A metals, right? Remember, the reaction here consists of a metal reacting with a hydrogen-bearing compound and generating hydrogen gas, right? So HC could be an acid, could be water. So for example, calcium, if you put it in water, it generates hydrogen gas and it becomes the calcium ion. Now, if we look down the periodic table, we'll find that these metals essentially are being asked to lose 2 electrons. That's the metallic character. So beryllium, for example, does not react with water. Magnesium does not react with water unless you vaporize the water. So you put it in steam, then it'll work. So calcium, strontium, and barium, they will react with water. In other words, based on this metallic character, you can see that there is an increase in reactivity in this property as you go from top to bottom within that group. Now remember, again, what we're actually measuring here is how well does this particular metal lose electrons? How easy is it to remove electrons from this metal? Please keep that in mind. All right. Let's make a jump here to group 4A elements. Now remember, group 4A spans all the way from the nonmetal carbon through the semi-metals, silicon, germanium, all the way to the metals, tin and lead. Now, of course, tin and lead will react with acid, whereas carbon, silicon, germanium will not. So carbon, silicon, and germanium are reluctant to make cations in the first place. They don't want to lose electrons, whereas tin and lead will give up electrons to displace hydrogen. In other words, in this case, the increase in activity is such that you are going from total non-metal carbon to total metal lead and tin. The metallic character is very dramatic here. If we were to put this on the table, across the periodic table, you can see again that within any group, yes, there's an increase in the metallic character as you go down the group. In other words, as you go down a group, it is easier to remove electrons from that atom. As you go from left to right, it decreases. So you have metals on the left side, non-metals on the right side. Again, it is progressively harder and harder to remove electrons. Again, remember what we said, which electrons are being removed? Well, technically, the electrons being removed are going to be the valence electrons. And we actually have a measure for this property. It's called the ionization energy. And it's defined as the minimum energy required to remove an electron from a gas atom in its ground state. In other words, the most stable electron configuration, the one you get if you build up an Aufbau diagram. So let's say that I have, for example, element X in its gas form. I'm going to input some energy, i.e. 1. I'm going to call this the
first ionization energy, and I'm going to take off an electron. Now, I could take that product, that ion, the X plus, and take off another electron, and we call that the second ionization energy, and so forth. We can have the third ionization energy. Now, what is important to remember is every time you take an electron, it becomes harder to take the next one out. Therefore, the first ionization energy is typically lower than the second one, which is lower than the third one. This might remind you a little bit of Einstein's proposal when we talked about the photoelectric effect, right? So essentially, the first ionization energy is similar to what we were calling back then the binding energy, or phi, except that in this case, it's defined for a gas atom. And by the way, if you go into your Canvas module for this unit, I have one, maybe two videos in there where they show you some ways that you can use to calculate what the ionization energy is, particularly the first ionization energy. Okay, let's look at the trend now. Let's plot the ionization energy of elements according to their atomic number. And this is going to be just the first ionization energy. Once more, you see these trends. And if you look across periods, you can see, for example, let's look at period 2, from lithium to neon. You can see a progressive increase in the ionization energy. Similar for sodium going to argon. Now, if you look within a group, for example, lithium going to rubidium, you can see a downward trend. So as you go down the periodic table, you find that it's, lower and lower ionization energy. Don't forget, ionization energy is kind of a way of measuring how easily can I remove an electron from that atom. The lower the ionization energy, the easier it is to remove an electron. Here's another chart which shows you more clearly these trends, and you can see how for any group, as you go down the group, you have a progressive decrease in the ionization energy. In other words, it's easier and easier to remove electrons. Whereas within a given period, you have a progressive increase. In other words, it's harder and harder, such that, for example, by the time you get from on any period out here into this, oops, sorry, out is into this area here. Remember that, oops, see what's going on here. Into this area that we had called earlier the that little zigzag line. As you cross over that line, you are basically in the territory of nonmetals. In other words, elements that will basically not want to lose electrons. So maybe the way to look at this is just to think about it this way. All right, think about it this way. When you look at these, consider that within a period, you essentially are, from left to right, increasing the effective nuclear charge. In other words, that electron that I'm trying to remove is getting progressively pulled more tightly into the nucleus. It's feeling a stronger attraction to the nucleus. Therefore, it makes sense that within, for example, a period, as you go from left to right, with the effective nuclear charge increasing, you're going to have an increase in the ionization energy. It becomes harder and harder to pull off that electron. However, within a group, remember, that electron we're trying to remove is farther and farther from the nucleus. It is feeling less and less of that nuclear charge, and therefore it is easier to remove, which explains why down a group, the ionization energy therefore becomes, oops, sorry, becomes smaller. Let's consider, for example, a group here, let's say period 3. Remember, these elements in period 3 have a completely filled n equals 2 shell, right? And so it makes sense that as you add electrons, they have a increasing effective nuclear charge. Now, there's two blips in here. All right, let's look at the first one. Again, we always have exceptions, right? There's a black sheep in every family. And here's one of them. Notice the transition when you go from beryllium to boron, and also from magnesium to aluminum. Kind of breaks the trend in there. So in terms of going, instead of going up, it goes down. So let's see if we can explain that very briefly. Here is the electron configuration of beryllium and boron on the left. Notice that beryllium has a completely filled 1s and 2s subshells. When I take an electron from here, what I'm doing is I am having to remove an electron from that already filled sublevel. So what would happen is, therefore, that I'm going to have more energy. In other words, that subshell that is filled is good in stability, so it's lower in energy. So going to a status that now removes that electron, it's going to take more energy to take it out. Boron, on the other hand, has that filled 1s and that filled 2s subshell, and its one electron is all by itself in a 2p subshell. So it makes sense that taking that out will give us, I'm sorry, what happened here? Oh, wait a minute. I'm missing a line in here. Okay, well, basically, it makes sense that therefore that in going from here to here, right, you have a less energy cost. Let me see if I can use this. So lower energy cost. All right. So that explains that blip. All right. And there should have been some text in here, just didn't come up. Okay. Our next blip is over here in going from nitrogen to oxygen. Also happens if you go from phosphorus to sulfur. Again, let's see if we can explain this, guys. Okay, here are the configurations for nitrogen and for oxygen on the left. Again, remember, we're not asking to form the typical nitride and oxide ions. We're asking to remove an electron. Notice that nitrogen already has a pretty stable, right? Has a pretty stable 2p sublevel according to Hund's rule, right? And so when I remove an electron for there, I am breaking up a pretty stable energy set. And I don't know why it's not coming up here. Sorry. Anyway, so what I'm saying is that this guy was pretty stable. And so I'm trying to break up something that's rather stable already. Now, if you look at the case of oxygen, uh, we already have a situation here where we have two electrons already in the same orbital. And it means that although the spins are paired, there is more repulsion because they're confined in a smaller region of space. And therefore, because they're repelled already, it makes it easier to remove, and therefore it results in a lower cost of energy. All right. Okay, so that's our explanation. So like I said, we are not dealing with the math of all these things. Remember, these are wave functions. All of these diagrams are essentially graphic representations of something that is actually generated by some heavy-duty mathematical calculations. And we don't have those with us. So we're trying to kind of like do a hand-waving type of explanation for this, just so it makes sense. But be aware that you can mathematically show these things and actually prove what these energies are and where they come from. Okay, trust me, guys. Okay, trust me. Um, Now, we have only talked right now about first ionization energies because they're sufficient to give us, an explanation of the trend. Remember that when you remove an electron, the remaining electrons are now going to be exposed to a much, much stronger effective nuclear charge, right? There's less electrons in there to cause repulsion. There's a stronger balance, more let's say, an excess of positive charges versus negative charges now. And so that means that taking out a second electron was going to cost more to pull it away. So it makes sense that in all these trends, the second ionization energy, the third ionization energies are bigger. And you can get to the point where you're trying to actually remove core electrons, which are very difficult to remove because those are the ones that give you a lot of stability. So for most of the discussions that we have about these chemical properties, we typically only focus on the trend in first ionization energy. And we'll talk about this more later on when we talk about the formation of actual compounds and ionic bonding. All right. So keep that filed away and remember where it is so we can come back to it. All right. Okay, the last property we're going to discuss very briefly is called the electron affinity. So whereas ionization energy is the energy required to remove an electron, electron affinity is going to be the energy change that happens when an electron, when an atom accepts an electron in the gas state. So let's say I have element X in the gas state and I'm going to add an electron, all right? That's going to be the step that defines it. Now, remember what we said in our thermochemistry discussions. We said that any reaction that essentially leads to the formation of a favorable interaction is exothermic. In other words, the final state is more stable, it's lower in energy. So for example, for fluorine to add an electron to form the fluoride ion, we said that the fluoride ion is the more stable form. So if we were to actually calculate delta H for this, it would be minus 328 kilojoules per mole. Okay, some authors will say that this delta H is the electron affinity. Some authors will say they'd like to take just the absolute value, or let's say actually the negative of this, and say that the electron affinity is 328 kilojoules per mole. In other words, what is the energy involved in making this thing? How stable is this thing? What kind of energy would I have to put in to take this electron away? So what I'm going to recommend is when you read any textbook, make sure that you understand which of these two definitions the author is using. Sometimes they will call this the electron affinity. Sometimes they'll take the negative of it and call that the electron affinity. Okay? Notice that for oxygen, the formation of a singly negatively charged ion has a delta H of minus 141 kilojoules, whereas the a different author might say the electron affinity is the negative of that. All right. Here's the thing, guys. Uh, Electron affinities per se are not present in as strong a trend. In other words, the trend in electron affinities between groups and periods in the periodic table are not as tight. They're not as well defined as they were before for the atomic sizes and for the ionization energies. All right. So I would say that in general, all that is important here is to say that halogens have the highest electron affinities. Okay, you can see them all here, right? In this trend, again, electron affinity versus atomic number. I think that's what's really important, is to know that halogens have very high electron affinities, which explains why they so readily form those, negatively charged ions, fluoride, chloride, bromide, etc. Okay. All right. So remember that when we are forming an ionic compound, which is what we've studied before, you have a couple of things involved here, right? Actually, several things. Number one, you have the how stable would an atom B by becoming isoelectronic with a noble gas. So that kind of like drives the particular atom to form an ion. Uh, then you have the idea of, how easily does a particular metal lose electrons versus how easily does the corresponding anion want to gain electrons. And there's another aspect that we'll discuss in a future chapter, which is what about the actual stability of forming the compound itself? All right. We'll talk about that in a separate lecture. Okay, time to wrap it up. Here's what we learned. First of all, ionization energy is the measure of an atom's attraction for its own electrons. The larger the ionization energy, the harder it is to pull electrons from an atom, which means the stronger the attraction that atom has for those electrons you're trying to remove. Secondly, electron affinity would be the measure of an atom's attraction for additional electrons from another source. How easily can I add an electron to an atom from another source? The general trend is metals have low ionization energies, which explains why they form cations more readily. And nonmetals have high electron affinities, which explains why they more readily form anions. All right. So I hope that covers the topic. Don't forget, if you have any questions, since this lecture, you're watching it asynchronously, any questions you have, please send them to me either by text or via Canvas messaging or to my email, and I'll try to respond as quickly as I can, okay? And if I don't, please forgive me. I'm trying to juggle several things here, but I'm trying my best to make sure I get back to you, okay? So please don't hesitate to ask questions, all right? This ends unit number 8, and don't forget that we will proceed in our next live lecture to unit number 9. We're gonna talk about the actual structures of molecules, all right? Well, have a great time, stay safe, and hey, make the most of the life you live. And don't worry, we're gonna make it through all together, okay? Thank you very much. We'll see you soon.